um we sorry so signaling and modulation, we have something called transmission mediums. So a transmission medium is going to be the physical channel uh on how signals are going to travel to different nodes and communicate with one another. So all network signaling is going to have some sort of electromagnetic radiation. And so electromagnetic radiation means transmitting signals as electric. We can transmit signals as electric current, infrared, light, or radio waves. So different types of transmission media can be either cabled or wireless, right? So in a cabled one, we have a physical conductor, right? So either copper or fiber optic cable. It's also called bounded media. Um, I guess because it's the signal is bound to that wire, right? And then we have wireless, and so they call that unbounded, right? It makes sense because it's not really bound to anything but the radio waves in the air. It uses stuff like microwave radio and all sorts of different things. Um, then we have the digital data. So that's discrete binary values. So that means zeros and ones. That's how information is represented. And so many of these transmission media and network products are going to support something called digital signaling. So digital signaling is going to use something called line coding, which is basically a series of pulses, right? So these pulses could be high or low voltages, or they could be on and off transmissions. And this is going to represent the zeros or ones, right? This is representing the binary data. So this makes transmission less susceptible to interference, and it's easier to regenerate these over large distances. So everything we do, right, is zeros and ones, and well, for the computer's sake, right? And so it can send these signals by just turning flashes of light on and off, right? So that's how that gets traveled through wherever the world. What's it? Fiber optic cabling requires like really wide loops, because if it's not a wide loop, then it's not going to have, the light's not going to hit, and you're going to miss that little signaling. Next up, we have. Oh, did I miss anything over here? So there was analog signaling as well. That's it oscillates over waves. So it's an analog signal. They're not really using that anymore. Everything was pretty much changed to that, but there was a frequency range to that. So just something like 800 hertz into 8 kilohertz. And that's within voice range. And so that's kind of how they were getting calls through. But everything had to get transformed over into digital not too long ago. 5. Bandwidth, baud, and bit rate. So we have bandwidth. So bandwidth is the range of frequencies available to a communications channel. And so this is going to be something, a digital signal uses something called baseband transmissions. And that means that the complete bandwidth is available on a single channel, right? So sometimes they put channels together in order to get like a higher throughput. So when we're discussing channel capacity, then they measure bandwidth in something called hertz, and that represents the number of signaling cycles that can be completed a second. So we could have 1 per second, and that's 1 hertz. And then we can have thousands per second, which would be a kilohertz. And then we got millions, which was megahertz, and billions, gigahertz. And then we have trillions, which is, I don't even know what they call it, but it's THZ. And then so if the specific medium supports a range of frequencies between 0 and 100 megahertz, then it has a 100 megahertz channel bandwidth, right? And so a lot of wireless radio transmits in the frequencies between 5,040 to 5,160. So it has a 20 megahertz bandwidth. So when we have a greater range of these frequencies, right, then we can carry more information per second. So what were they talking about? So if we had, so that had a bandwidth, they had a 20 megahertz bandwidth on the wireless radio. However, if we have like 100 bit bandwidth, we have a whole lot more. So when they're talking about bandwidth in data communications, a lot of times they mean data rate, and that's the amount of information that we can send per second. And so when talking about that, we have to also think about something called the baud rate. So the baud rate is the number of symbols. So a series of events, communication channels. A symbol is a signal that is transmitted over a channel in a series of events called symbols, right? And the symbol could be a pulse. It could be electric current. It could be the transition between a peak and a low, right? And so the number of symbols that can be transmitted per second is the baud rate. So baud, once again, is going to be measured in hertz. And then we have the bit rate. So the bit rate, sometimes you'll see this BPS. This is the amount of information that can be transmitted, measured in bits. So in order to transmit information efficiently, we might try to get that bit rate as high as we can. All right, so distance limitations. So the loss of signal over over distance is usually called attenuation. This is the loss of signal strength, and this is going to be measured in decibels. And decibels are going to be the different the ratio between the signal strength at the origin and at the destination. Then we have noise. Noise is getting unwanted transmission data interfering with our signal. And then they express this with a signal to noise ratio. I have to look at how that's calculated. All right, so transmission media types. We have copper. So copper is used to transmit electrical signals. And so the cable between two nodes is going to have an electric current going on. And then so that's able to send those pulses down to make sure that we get whatever information we wanted to get. And there are two main types of copper. We have twisted pair and coaxial. And so these electrical signals are going to be susceptible to interference and dispersion. So we want to make sure that we have the right cable for whatever we're dealing with at the time. Copper cable definitely suffers from attenuation, so there's definitely a loss of strength over a period of length. If you plan on taking the test, you need to know those. If you plan on taking the networking test, you need to know which cable you are going to use for different distances, because that's on the test. I just don't recall what they are this time, but they have nothing to do on the security. You won't come across them at all. Fiber optic cable. So this is going to use light signals, and then the light signals aren't really susceptible to interference or noise. So they have a higher bandwidth than copper cable can actually get. And then we have wireless radio. So we have RF, so that's radio frequencies, and this propagates in the air, sending stuff to antennas and things. And there's the International Telecommunications Union, and so they use a bunch of different frequency bands and you have to get a license from the government to get that. So a lot of times they'll start selling spectrum to I think Clearwire or somebody had a whole bunch of spectrum they auctioned off, and that's I think a lot of what spectrum is available has a lot to do with the upcoming emergence of 5G. And then this is going to be susceptible to interference. Why? Because it's radio waves. All right, so media access control and collisions domain. So media access control is meaning the device. So multiple access, media access control is going to refer to the methods a network technology is going to use to determine what node can communicate on what media and deal with any problems in that. So we might have like two devices trying to communicate at the same time, and in that case we'll have like token passing and stuff like that to make sure only the person with the token can speak at that time. So the person meaning the device trying to talk. And so this is called deterministic media access. So we're going to have a central device that's going to say, okay, how long each one of these nodes are allowed to transmit. So in a token ring, the ability to transmit is going to be determined by a token, and that is going to pass from each node. And so it's kind of like passing that, I don't know, you've seen movies or maybe in elementary school, like they passed something around and you had to hold the stick if you were able to talk. Something like that, right? So this is going to benefit real-time systems such as industrial settings or places where they, chemical storage facilities where they need to have a guaranteed transmission time. Then we have contention. So contention base is going to be where each node is going to compete for the use of transmission media. So a collision domain includes all the hosts that are on a specific segment or connected to the same hub. Like, so these are all in the collision domain, and these are all in the collision domain. And so when two of these nodes transmit at the same time, we have the possibility for a collision, right? And then they have to resend, and that will reduce our bandwidth. And then even when they keep on resending, there's potential for more collisions. So collisions are going to, and performance are going to decrease as more of these nodes are added. And so so this is our picture. Here's a node, here's a node, here's a node, here's a node, here's a hub. So this is the one collision domain, and this is another collision domain. And so only one of these would be able to speak at a time, because if their packet or whatever crashes, they have to resend it. And so if they all keep on having resend stuff, then there's the possibility for more collisions. But luckily, there's really not too many collisions anymore. A lot of the Network Plus is dealing with older technologies. Then we have CMSA CD. So that is, well, let's talk about this first. So Ethernet protocols that are deciding contention and media access are called carrier sense multiple access protocols. And so we can have things called half duplex. So half duplex is a node is able to transmit or receive, but it can't do it at the same time. And then full duplex, they would be able to. Then CMSA collision detection is, it's gonna it detects when a collision has occurred. So it defines methods for detecting a collision on different types of media. And then so if there is a signal present on the line, it would be able to detect a collision and kind of broadcast a signal, which is called a jam signal. And so each node that was attempting to use that media, use that wire, would have a random period to back off before attempting to transmit a signal again. Right, so they're trying to avoid collisions here. So each one of them, each node in our thing, if there is a collision, they're going to get sent a signal telling them to back off and wait until they're clear. And then we have carrier sense with collision avoidance, and so this is going to use something like a request to send, and so the nodes are going to listen and wait for their turn, a clear signal, and then they can send whatever they wanted out. And then we have switch networks. So switch networks, they eliminate the effect of collisions. So this problem basically with contention and crashing into each other is overcome by switches. So a switch establishes a temporary circuit between two nodes that are exchanging messages. And so using a switch means each switch port, because you have ports on a switch, right? And so each port is going to therefore operate in half duplex mode, and so collisions will only affect that port. So we can also allow for full duplex transmissions in which they can send and receive at the same time. All right. So this is one checking the network to make sure they can talk, and then they transmit the data. So here, data to transmit. They check the data. The data is transmitted. However, they end up with a collision, so now they have to wait and retransmit that data again. All right. So broadcast domains. Broadcast domains. Within a collision domain on any shared medium, or all the stuff on a collision domain, any given node will receive all the traffic within that domain, right? So they all get the same signal, right? And so it chooses to process only traffic that's specifically addressed to it. And so this is going to be referred to as unicast traffic. And so everybody else is just going to ignore that signal unless it was meant specifically for them. And then it's useful to have a mechanism that can also transmit the same traffic to multiple nodes. And so this is broadcast traffic. So this is meant for everybody. So this is used, they accomplish this using a special destination address. And then broadcast traffic is often used basically when like the host needs to discover another host and it's like trying to configure a list or something like that, right? And get updates, things of that nature. So nodes that are in the same broadcast address are said to be in the same broadcast domain. And then bridges, so this is gonna be a layer 3. Bridges and switches are normally flood broadcast traffic, meaning that they send it all out to everybody. And then when a broadcast domain is defined in logical networks at layer 3, then it typically has the same boundary that it had on the layer 2 on the switch. So so the model is trying not to be restrictive. We can have VLANs that can do this for us, that can switch this and separate these broadcast domains virtually. All right, so our first activity is 2-1, and it's discussing media types and access methods. So take about 10 for that, I think. Let's do about 7 minutes for it. Itself, There's been a lot of different technologies and media access abilities and stuff, but the main one still around is Ethernet. So it is the only mainstream one nowadays. So Ethernet supports a wide variety of media options, and it's all pretty inexpensive to handle. So it was created all the way back in the 60s, and it was used by Xerox and Intel and stuff in the 70s. It uses for the frames themselves, it uses a preamble. So a preamble and a start frame delimiter. That's the preamble here, and start frame delimiter. So this would be like a model of a frame, right? And so the preamble and the start frame delimiter are used for synchronization for that CSMA CD protocols for identifying collisions. And then the preamble is going to have 8 bytes alternating zeros and ones, and the start frame delimiter is going to have 2 ones at the end. We just need to know that the preamble is basically to help with those collision stuff. All right, and then we have the addressing. So we have the destination and the source for the MAC addresses for when we're sending and receiving things. So that's media access control access addresses. And then they have their own unique identifier for the Ethernet interface on them. So MAC addresses are going to be they're also called local or hardware addresses. And those come in 48 bits. All right, so frame length and maximum transmission unit. So the 802.3 standard has like a 2 byte field to specify how big the data or the payload is going to be, and so this can be between 46 and 1500 bytes normally, and so the upper limit of that is called the maximum transmission unit, the MTU. And then we have coding and payload types. So the coding and let me go here instead. This makes more. All right, so we can have a minimum frame length. We can also have a jumbo frame. The minimum frame length is going to be 64 bytes. A jumbo frame is some like gigabyte and gigabyte Ethernet products can support jumbo frames that have a lot bigger MTUs than normal. But they're not really standardized. When it comes to the coding, the coding payloads are usually an IPv4 will be like what the hex value, so 0x0 is 800, and then IPv6 has its own. It's 0x89DD. You don't really have to worry about that. But since it's on here, I'm just gonna say what it was. And then we have error checking. So error checking, this is one of the fields that are on that frame. So we can have cyclic redundancy checks or a frame check sequence. So the cyclic redundancy check is going to be calculated based on the contents of a frame, and however, there's no mechanism to retransmit if there is damage to a frame. So I don't really see the point of it really, but it checks. It knows that if there was an error at least. Ethernet deployment standards. So we have several different Ethernet deployment standards. So we can have these are going to be like based on distances. So like this X base Y, this is going to have things like the bit rate in megabits or gigabits per second. The baseline, baseband broadband transmission. So that's whether it's using baseband or broadband, but all Ethernet is going to use baseband. And then they got a designator for the whatever media type is. So that's that convention for when they're speaking about it. 10 base T is working at 10 megabits per second on a single twisted pair network, and it was used with hubs and bridges and stuff back in the day. Fast Ethernet. So Fast Ethernet was an update to 10 base T, and it uses CSMA CD stuff as the other one did. However, they have better frequency signaling and higher encoding methods, and it raised it from 10 base to 100 base, right? So 100 base is going to refer to Fast Ethernet working over Cat5. Cat5 is a type of cable, and you can have Cat5 or better, and it will be either be a twisted pair. Twisted pairs mean the cables are twisted over each other, and that's supposed to help with not getting any electromagnetic interference, and unshielded twisting pairs. So the shield acts to help. The shield being plastic, you know, you've seen them. They have like little rubber coatings around them sometimes on cables. So that's trying to shield it. Or sometimes it's like aluminum. And then so hubs and bridges are replaced by switches nowadays, because Fast Ethernet only allows for 1 or 2 hubs. So this doesn't really apply if it has a backbone, but really they're not really using hubs anymore. They're deprecated. And then we auto negotiation of link properties. So auto negotiation is going to allow different devices to choose the best connection parameters. So whether that be 10 megabits per second or 100 or full or half duplex. So in this case, it could negotiate that. I believe it goes redundantly. It goes and it chooses the if we have 2 networks connections and one of them can only operate at 10 megabits per second, then by default it'll knock down to the 10. Gigabit Ethernet. So Gigabit Ethernet is going to build on top of Ethernet and Fast Ethernet, and it's 10 times faster than Fast Ethernet. And that's 802.3z. It's usually the fiber. It's going to be a fiber thing for the most part. Well, a lot of times to get it to work good, especially over distances, they'd be called 1000 base SX or 1000 base X period for fiber optic, and then they have SX for LANs and LX for WANs. And then we have the twisted pairs, the 1000 base T and TX. So 1000 base T can only go like 328 feet. 1000 base TX, I'm not sure about that one. I know there's 1000 base LX, and that can go like 3 miles, 1,800 feet. But the one that moves the best is not these copper cables. It would be fiber optics. Technically, those could go for miles. And it's going to use switches only. Then we have 10 gigabit Ethernet. So this is going to multiply gigabit Ethernet by a factor of 10. So it's not really deployed out there like that. It's less likely to be deployed for general purposes, right? This is probably going to be like a major company, such as film and TV producers or government organizations. So 10 gigabit Ethernet is got several different standardizations. We have the 10 base T, and so here that's local area copper. I think the best you can get is between 180 and 328 feet with that. Then they have 10 base SR, so that's local area fiber. So you can go anywhere from 1,000 feet to 6 miles. And then the last one, the wide area fiber, It's 25 miles. All right, so you have your next activity. You could take I don't know, 5 to 10 minutes for this one. Network interfaces. This deals with the exam objectives of explaining the concepts and characteristics of routing and switching. And given a certain scenario, use whatever appropriate tool. So we have network interface cards. This is a transceiver. It has a component which is a transceiver component, and this is responsible for physically connecting the node to it, right? So like physically plugging it into the Ethernet jack, stuff like that, right? So this is all implemented in the network adapter, network interface card. We have a media type for each one, and then there's going to plug into it. So depending on what it is. Then we have media access control hardware addresses. So the MAC address is 48 bits, 48 binary digits. And then the format of the number is going to differ based upon whatever type of system it is. So it's usually going to be displayed in 6 groups of 2 hexadecimal digits, and each manufacturer is going to have a range of numbers for them, and they're going to hard code a unique number to it, right? And that's called the burn-in address. So the first 6 hex digits are going to be called the organizationally unique identifier, so OUI, and this is the identity of the manufacturer of that adapter, right? And then the last 6 digits of the MAC address are its serial number. So first 3 are its manufacturer, last 6 are its serial number. So we also have something called an extended unique identifier. It's sometimes referred to as an Ethernet address. It's its own unique address. It's kind of like a MAC address. All right, so MAC address formats. Oh, that's what we just went over. So we have, that's the layer 2. It is layer 2, and it's defined by those standards. We can see it's 48 bits, so that's 6 bytes. And then the extended unique identifier 48, the MAC address is going to be, so it's kind of UEI is kind of interchangeable with this MAC address. The idea of it anyway. So the UEI is technically this, but so is the MAC address. Just know they kind of refer to the same thing. So the UEI 48 is going to be represented by those 6 digits. And then this part is going to be the UEI 48, and then the other part is the serial number. So this half of the MAC address is the UEI 48. All right, so MAC address formats. Usually they're going to be burned in, and then they're administered in addresses. And then we can have individual and multicast. Multicast, it can cast it to certain people, multiple people at the same time, whereas the unicast would only be one. So the frame is destined for a single destination interface in unicast. So we have our shared Ethernet, and then all the interfaces receive the same frame, in this case, in shared Ethernet. However, they're going to ignore it if it doesn't have the correct MAC address on it. And then if we were on a central device, if that central device was a switch or something, then only the server would get the unicast packet, and then it would track down what exact MAC address it went to and send it to the right port, right? And then we have broadcast. So broadcast broadcast the data to all other nodes on the network. So hubs and switches can flood broadcast to every port except for their own, because they're aware of themselves. And then a frame uses the destination MAC address. So we have remember the first three octets are going to be for the organization, and the last are going to be the serial number. So in this case, we have the server, and I guess he's sending something out. Wait, hold on. No, the source here. This is the source. They are sending, trying to send something to this server. Everybody's going to receive it because this is a hub, and a hub sends the same thing to everybody. However, since they're not addressed to them, they drop it. They don't care, and only this one will keep it. And that would have been unicast. What's going on here? So ARP. So when hosts are communicating with TCP/IP, IP address is used, and at the network layer to identify each one of these hosts. So transmission of the data has to happen at the physical and the data link layer, and they're going to use the MAC address, right? And so the TCP/IP suite has address resolution protocol to perform the task of figuring out what IP address is matched to what hardware address, right? So when we have sending and receiving hosts on the same network, then they're gonna work like what we have in this picture. So at 1, right, we have the destination 10.0. Wait, that's not 1. We have 1 is here. This is the sending host. So the destination IP address has been determined, and it's going to figure out that it's a local one. So it's going to check its ARP table cache. So they will have these mapped out IP addresses to MAC addresses, and they will have them in a table, and they will try to look up where this person is located on the network. So if the MAC address is not actually present on its cache, then the ARP is going to make a request and broadcast it to everybody on the network, right? And then the broadcast is going to be processed by all the hosts on this local segment. And if it doesn't recognize, and so if the request contains its own IP address, then most of the hosts are going to ignore it, right? And if the target does recognize its own IP address, then it's going to update its cache with the MAC address of the host. And then the source is then going to receive a reply. It's going to update its cache table, and then we can make our connection. So he's going to ask who has 10.0.0.11 and tell me down here. And so if we see that this is our local IP or private IP, this 10. Whatever, it's not going to look out into the vastness of the internet. It's going to look in here and try to find out where this host is located so we can begin our connection. All right, so in this one, we have a host on a remote network. So this is outside of our network. The other one was inside of our network. So in this case, the destination IP address is determined to be a remote one. It can look at the IP and decide that it's a remote one, because usually our local ones are going to be 10. something or 192. something. So the host examines the ARP table and for whatever IP MAC address of this gateway. The gateway is the router to the internet world, right? And so if the mapping for the gateway address is not found in the cache, then it's going to broadcast an ARP request to find out where our gateway is. not for the remote destination host, but for our gateway. So hopefully we're able to find our gateway, and then we can get connected to our gateway, which is our router basically for you guys at home. And then at the router, then the router is going to determine whether the destination was going to be for locally or not locally. And once it finds out it's not local, it's going to forward it out based upon that IP address. All right, so there's something called the ARP cache utility. So an ARP broadcast is going to be cached in an ARP table, and then if the entry is used within a specific time period, the entry is going to be held in the cache before it gets deleted. So entries in the cache are usually timed out after a certain amount of time. Maybe you've changed the network card or something like that. So the cache is reserved in memory that contains our IP, internet addresses, and our physical addresses. And so before the ARP broadcast is performed, then it's going to check the cache every time to make sure they have the correct MAC addresses mapped out to each IP address. Because these local addresses are leased from your IP from DHCP, and so these can change after a certain period of time. And you see this says dynamic, that means it changes. Static would mean these IPs will never change. But so it has to periodically make new lists. So we have different tools you can use, command line tools for the ARP. And so ARP-A on the command line is going to show you the contents of the ARP cache. You can use this to find out what you really have, what the associations on your network are between MAC addresses and IP addresses. ARP-S, this is going to add an entry to the ARP cache. And then we have, so you can add your own entry to it. And then we have ARP-D, and this will delete things. Well, this star specifically means all, and it'll delete everything in the ARP cache. All right, packet sniffers. So a packet sniffer versus a protocol analyzer. So a packet sniffer is used to support a protocol analyzer. So it allows us to get all the packets that come out, right? A sniffer captures the frames that are moving over a network, whether it's cabled or wireless. And you can use a network card driver for it to do that. Or you could use a tap. A tap meaning literally just like tapping people's phones. So you would put a tap on a network as well to see what type of packets are going through it. And then so when we capture these frames, we can see what's going on. And then once we have these frames, we can look at it through a protocol analyzer, and this protocol analyzer will allow us to analyze their traffic. We could see what time connections were made, what websites you went to, the stuff you downloaded, things you wrote, everything, if it's not encrypted. So you're going to get a chance to get really familiar with packet sniffers and protocol analyzers as this class goes on. So most packet sniffers, they can work in promiscuous mode, and so they'll capture a lot of traffic that may not necessarily be meant for them. So that's what promiscuous mode is there. Or you can use mirrored ports. So a mirrored port is we would try to capture traffic intended for another host, and by configuring a spanning or otherwise known as a mirrored port, and that would like kind of forward the traffic to us as well, like on our to wherever we're trying to, we're trying to watch them. So they receive their information that they want, but it also mirrors it back to us, so that way we can read whatever's going on. All right, TCP dump. TCP dump is a command line packet capture tool for Linux. So this says TCP dump interface ETH0. ETH0 is the interface that we listen on our computers. That's what it's listening for, traffic meant for your computer on the internet. So it will continuously capture packets until you actually stop it yourself. So you could put -W or -R to switch and write or read the contents of captured packets or files. And then they have filter expressions, so we can filter this stuff out by what type of packet it is, where it's going, what type of protocol it's using. You could use Boolean operators, so Boolean are and or not. That'll be Boolean operators. So you could say I want stuff from this IP address and this IP address, or you could say I want something that is not this IP address, right? But I want everybody else's, because maybe I know what this IP address is about. Maybe I know that's Bob, and I know Bob. He's a cybersecurity guy. He's fine. He's not who we're looking for, or something like that. I don't. All right. So your next activity, you have one more activity you can do. These last two you will not be able to do because we do not have our labs that used to be at Gaithersburg because of our whole situation on being online now. But you can go ahead and do discussing network interface configuration and monitoring. And then after that, we will reconvene and we will look at anybody who has been unable to get their virtual machines up and running. Does anybody have any questions? No questions. Everybody's good. All right.